Hey, welcome to this new episode of Coding with the B team. Unfortunately, this week I'm not able to do a live stream, so rather than not doing anything, I thought I would record a video and publish it. Um, I was going to write a prototype anyway, so yeah, let's just record the process and publish it because I think that's an interesting topic for the community. If you follow us on GitHub, you may have seen this protocol RFCs repository, and basically that's our way in the IOTA Foundation to propose and approve changes to the protocol. So if you go in the text folder, you may see things you recognize. For example, the white flag RFC and the weighted uniform random tip selection RFC. These are changes that will be part of Chrysalis Part 1. So yeah, if that's something that interests you, you can just have a read at the different RFCs. But yeah, what I wanted to speak about today is something that will be part of Chrysalis Part 2, and that is the new transaction layout. So just two days ago, we opened some new RFCs. So what I'll do today is to have a look at them, explain a bit the layout, and most importantly, do a prototype of this new layout. I think I missed one, so I'm just going to open them again. Yeah. So in the B repository, we have this B transaction crate, which is where we have everything related to transactions. So the transaction format, the format of the different fields, the serialization and deserialization of the transactions, that kind of stuff. But you can see that at the moment we have only one module, which is called bundled. If you know the way transactions work at the moment in IOTA, in the protocol, you know that transactions, value transactions, most importantly, to make sense, they have to be packed together in what we call a bundle, which is just a collection of transactions. So the new layout, the new format of the transaction that we call atomic transaction is because, well, they are atomic, which means that they are self-contained. So they don't need another transaction to make sense or whatever. So they make sense by themselves. So what I'll do is to create a new folder called atomic. Inside I will put a file mod. Yeah, so a warning, I currently have a German keyboard because my laptop is being repaired, so I'll be doing a lot of mistakes today. Yeah, so let's rename that mod. All right, and in this one, let's expose it as well. All right, but you can see that we have something in the global scope. We have something called vertex, because even if we change the format of the transaction, something will always hold true, and that's derived from the Tangle architecture, which is a directed acyclic graph, but most importantly, each transaction validates or approves two other transactions. That are commonly called trunk and branch. So yeah, that's what a vertex is in the Tangle. So if, for example, I go to transaction, I may see an implementation of that somewhere. Yeah, here. So you can see that a bundled transaction is a vertex, and these methods basically just return the two fields, trunk and branch. So yeah, we'll probably be doing the exact same thing with our new format. But yeah, let's start with RFC 17, which is the base one. Why the base one? Because it's actually the vertex of the tangle. So I'm not going to read to you the whole content. You can do that on your own. But yeah, we'll just focus on the layout. So yeah, that's the main layout of the new transaction. So I just said transaction, but what may be confusing for you is that this is now called message. So what used to be called transaction is now called a message. You'll see why just a bit later. But message is our new vertex because you can see here parent1 trunk and parent2 branch. So yeah, the first field is a version byte. You will soon see that pretty much everything is this new format as either a version byte or a type byte. With that makes the whole layout way more flexible and extensible compared to the one we currently had, which is pretty much locked, and every modification would be a breaking change. So by doing that now, we allow ourselves to improve the layout without breaking changes. But yeah, let's do that. So new file, message.rs. Oops. Right, let's copy paste that. Let's, oops, nope. Yeah, I'm doing a lot of mistakes because of that keyboard. Alright, so mod message. Yeah, let's create that structure. So pub struct message. We already know that our message is our vertex, so we know that we can already use vertex. Oops. Vertex. Alright. And we already know that we are going to import vertex for message. Alright. Yeah, so the first field is version. I'm actually not going to put that as a field in message because this should be outputted when you serialize and deserialize, but it shouldn't actually be part of the struct itself because the whole struct itself would be changed if there was a version. So at some point we would just create a new type for this version. So the version byte doesn't necessarily have to be a field here. So I'll just keep this one for now. Yeah, so I'm going to create trunk and branch. Yeah, I'm probably going to have a lot of these things, so I'll just create so what is the message ID of the first message reference? Yeah, so I'll just create a type hash. Yeah, I should probably be doing that in another file, hash.rs. Right. So pub hash, and that would just be struct, and that would be you wait. Oops. You wait. How much? 32. What's happening? Oop, that's semicolon. All right, and then mod hash. Yeah, I'm probably going to expose this one. Oops, good use. All right, so vertex and then hash. All right, so this would be a hash. Then we have branch, that would be a hash as well. What do we have next? Well, we can already implement that. So we have fn trunk. So we need the associated type. Yeah, I put an associated type here because I'm not sure we are not sure the hash type will always be the same. So just being extra careful, probably not useful to be honest. We'll see later. So that's that, and then we return self dot self trunk. Oops. Where is the alright? And then copy pasting this one branch. Alright. The next one is payload length and payload. So yeah, so you can see that's the way we have this message structure to be extensible, because now we can create many kind of payload and put them in the message structure. So here, for example, we have a little list of possible payload. We have a signed transaction to basically exchange tokens. We have signed data to just send data, but with it being signed. Then we have the unsigned data payload, which is the same but not being signed. And then we have the indexation payload. Indexation payload is a way to have some kind of retrocompatibility with the way it is today, where you have this tag field and you can tag transactions. Here we don't have this tag anymore, so if you want to index something in database, you would have to have this payload as well. But yeah, what's important to understand here is that you can have payload and then you can have nested payloads. So a payload can itself have a payload. So in the case of indexation, for example, you can have an indexation payload inside of a signed transaction payload, which allows you to tag the specific signed transaction. So yeah, it's very flexible and you can do a lot of things. Yeah, so it starts with a length, payload length. On the same thing that's the version, I'm not going to put the payload length in the structure itself, because it should only be serialized and deserialized, but not be part of the actual struct. So when we are going to write the serialization and deserialization logic, this should be append as well. But here what's important for us is to just have a payload. Payload. So now the tricky part. The tricky part is that we have different kind of payloads. So how to represent that in a type? So the straightforward way to do that is to have an enum. But if you have a regular enum, then it will always be the size of the maximum size of elements. So it would just have the size of the biggest element in an enum. So if you are just sending a tiny payload, you would always fall back to the size of the maximum one. So we are not doing an enum this way, but what we'll probably be doing is to have an enum where all of the variants are boxed. So they would all have the same size, the size of a pointer. So it would probably come with some performance, being a little bit less performant, but at the same time we gain a lot of memory by doing that. So yeah, so what I'm going to do is to have a new folder called Payload, and I'll put all of the payload in there. So new file mod.rs. All right. Yeah, so I'm just going to create one file for each of the different payload. I see that one is missing there, the milestone payload. It should be here as well. So yeah. All right, then I can start doing that signed transaction. So new file signed transaction dot rs. Then we have signed data, signed data dot rs. Then we have unsigned data, unsigned data dot rs, and we have indexation dot rs, and we'll have milestone as well. Yeah, so now the cool thing is that we can do milestones just as a kind of payload, so it makes it way more easier to process than the way it was today. So just going to use that as well. All right, and now just creating some structs for them. So pub struct signed transaction, pub struct signed data, oops, all right, pub struct unsigned data, oops, pub struct indexation, and then pub struct milestone. Oops. All right, so now here I'm just going to expose all of them. So indexation, pub use, then pub use milestone, pub use signed data, pub use signed transaction, signed transaction, and finally unsigned data, All right, and I'm going to create the enum. So pub enum, I'm just going to call that payload. All right, so indexation, milestone, oops, signed data, signed transaction, oops, and unsigned data. Yeah, so the nice thing is that we are proposing some fundamental payloads, but now the community will be able to propose some new payloads that we haven't necessarily thought about. Yeah, so as we said, we are going to box them. So, all right. Box, whoops, box. So box just mean that they are on the heap, and the actual size of the type is just the size of a pointer. So now they all have the same size, and we don't have to worry about some of them taking more space than the others. Cool. So now I'm doing that, and here I can import it. So payload, and here, all right, now it's working. Just compiling quickly. Ash is not in the root. Yes, Ash is not in the root. Ash is in atomic. Oops. So should I do yes. Could not find payload in atomic. Yes, I am not exposing it. Payload. Alright, use of undeclared. Wait, what? Payload mode. Payload mode. Ah, alright, yeah, no, I did a mistake. That's not what I wanted to do. I wanted to do that. Yes. Alright. Not found in the scope. Yeah, yeah, actually I wanted to do both. Alright, yeah, my bad. So mode, yeah. Alright, it's fine now. Yeah, alright, so let's start implementing the layout of all of these things. In the main RFC, there isn't an example, which is the probably the most basic one, which is unsigned data payload. Since it's not signed, it's only the data, so it's only one field, and it's just some bytes. So unsigned data, and in Rust, that would just be a vector. So that's a vector of U8. Yeah, that's pretty much it. That's a payload. Now we never really finished the message format. So there was the payload, and then there is the nonce, which is just the proof that you have been doing the proof of work. Yeah, that's the proof of the work. So it's just an U64 there, nonce, and that is an U64. Oops. Alright, and that's pretty much it for the message. Trunk branch, a payload, and a nonce, and that's it. So I'm going to close this one. This is fine as well. Yeah, then I think that's it for the message. Just quickly reading if I didn't miss anything. I'm not going to go into details of the validation of that payload or that payload. Everything is explained in the RFCs. But yeah, just wanted to give a quick overview. Yeah, let's do the milestone one because that's a simple one as well. So yeah, if you know how the previous milestone bundle was, there is a MSS signature, which stands for Merkel signing scheme. So it's a Merkel signature built on top of WOTS. So currently in the mainnet, this needed 3 transactions. So yeah, now this is being done atomically, and that's just a payload. So the payload is pretty straightforward. There is obviously a type. As usual, we are not going to put it in the actual struct. So there is an index. You can see that even if it's an index, there is varint. Because it's not clearly defined at the moment what kind of integer it should be, and it also depends on the serialization primitives that we are going to use, but anyway, this is an integer. So this is index. So milestone, where is it? There. So index, at the moment I'm just going to put a new 32. Then we have a timestamp. All right, let's add a timestamp, pretty straightforward as well, which is a U64 keyboard. Then we have an inclusion Merkle proof. To better understand what that means, I redirect you to reading the RFC 12, and it pretty much explains why we need that. But this is due to the changes coming with white flag. So this is required now, but I'm not going to go into detail of that. So yeah, there is an inclusion Merkle proof. Merkle proof, which is 64 bytes. So this is an array of U weight and 64 U weight. Oops. Alright, and then we have the actual signature of the coordinator. Alright, that's pretty much it for the milestone. Yeah, indexation, I have it there, and as I said a bit earlier, that's basically just a tag. So very straightforward, nothing else than just 16 bytes. So yeah, U weight as well, and 16 bytes. So that's it. Alright, so indexation is done. Yeah. So unsigned data payload, we already did it. It's there. I'm just going to copy paste that. And the signed data payload is really similar, except that it is signed. So it has a public key and a signature of ED25. So public key, where is the word there? Which is a vector of U weight. Nope, it's not a vector, sorry. U weight and 32, no 32, yeah 32. Oops. And then we have the signature, which is U weight and 64. Alright, and that's it. So that's it for signed data, then signed transaction. So this is done, this is the hash, this is our payload, and this is the last one, and this is probably the most important one because that's the one that actually moves tokens. So this is Milestone, we did that. Yeah, and so this is RFC 18 if you want to read it. And it explains how basically it works. So if you have been following as well, you know that we are moving from the account balance thing to the UTXO management. So this will be part of the layout as well. Yeah, so let's start doing that. So this is the layout of a signed transaction, which is mainly composed of an unsigned transaction and a lot of unlocked blocks. Yeah, so let's start doing that. So rather than doing just a file, because there are a lot of components for this payload, I'm going to create a new module. So signed transaction.rs. Yeah. Oops, created a file, not a folder. signed transaction .rs, and it already exists then, so I'm just going to push that in, rename it. Alright, and then we have this, and it will be our mod.rs. Alright. So what is it composed of? Payload type again. Then we have this unsigned transaction. So since it has a lot of fields in itself, I'm going to create a new file. Unsigned transaction.rs. Yeah, and I just saw that I put .rs at the end of the folder. Alright, so we have this one. Copy pasting that. Alright, so pub struct unsigned transaction. So what is it made of? A transaction type again. Then we have a lot of inputs and a lot of outputs. So if you know how UTXO work, you just consume inputs and you create outputs. And an input is basically a reference to an already existing output. So you consume and create input outputs, and you can have a lot of input. You can aggregate them into one output if you want, but you can also create many outputs. Yeah, so inputs count. At the moment, I don't really care about the type of that, but I don't expect it to be very high, so I'm just going to put 2 bytes for it. So there is this one, and there is output count. Yeah. All right, and then we have the actual inputs, which are a vector of input, and we have output, which is a vector of outputs. All right, so we'll need to create input and output, and there will also be an enum, because they are probably going to have different types that would be allowed. So for example, input could be at the moment we only have UTXO input, but it could be something else in the future. So yeah, this will be an enum as well. Yeah, so for that purpose, I'm going to create an input folder and an output folder. A new file, node.rs. All right, copy pasting this one, and all right. Yeah, so yeah, okay, let's start. So this is basically done. What can this be? So an input. What can an input be? At the moment, as I said, it can only be a UTXO input, so I'm going to create this one as well. UTXO.rs. Alright, pub struct UTXO input. Alright, and in this one I should have mod UTXO. We'll use UTXO input. Alright, and we'll know that we'll have our enum, pub enum, that we call input, and oops, at the moment it's just UTXO being boxed UTXO input. All right, and here we have to use create atomic payload. So where are we again? Payload signed transaction input and input. Oh, all right. Yeah, I'm not entirely sure of that. So this is not triggering output not existing, so I may have not included something. So signed transaction is there, but then yeah, I haven't. All right, mod signed transaction, unsigned transaction, sorry. All right, so now this should not compile anymore. Yeah, all right. And then we have to, also we have to mod input, mod output. All right, so now we only have output missing. Cool. So let's finish UTXO. So we have input type, which is just the type of UTXO, so not including that anyway. So now we have transaction ID, which is a hash. So let's include that in UTXO. Transaction ID, which is a hash, and hash comes from use create atomic hash. All right, so we have that, and then we have a transaction output index. So output index, and that would be something low, I guess, U16. So what does it mean exactly for UTXO input? So I told you that an input is just a way to reference an output. So, and to be able to reference an output, you have to know the hash of the transaction, and within this transaction, which one of the outputs you are targeting, and you do that by the index. So yeah, if you want the second index of that transaction, you just reference the transaction and with the second output. So this is done, and that's basically the only input we have at the moment. And then outputs, we have this one that I'm going to create, new file, .rs. So this is seed locked single deposit.rs. All right, copy pasting that. So struct. All right, so what is this thing? This is basically just an output, so it means to what's the condition to have access to these tokens. So this first one is to describe a deposit to a single address, which is unlocked via a signature. So I'm going to send the tokens to a specific address, so an address and an amount, and to be able to unlock them, you would have to provide the right signature for it. So that's the only output we have at the moment. On the very same format, we have siglock colored single deposit, which is the IOTA way of handling colored coins. The RFC is not opened yet, but it will be soon. The format is really similar, but there are some more fields. So yeah, how does that look like? We have output type again, then we have an address that can be a WOTS address or an ED25 address. So this is new. You know that so far we have already been handling WOTS, and now we are introducing a new signing scheme. Which is very nice with this whole type thing, is that we can add as many signing scheme as we want in the future without breaking anything. So yeah, I'm just going to create some structs, pub WOTS address, and that is what is that? That's 49 bytes. Oops. What was that? Yeah. So that's weight, and that's 49. Yeah, so this is just T5B1 encoding, the one you are probably used to. That's the encoding of the network, that's the encoding probably of the database as well. So that's the way to encode 243 tricks in 49 bytes. So that's WOTS address, and now we have ED25519 address, which is 32 bytes. All right. Yeah, and I'm probably going to create an enum as well. Enum called address, and it will just be this boss address. So we have I think we can not we don't necessarily have to box for a couple of bytes. The difference is not that much, so we can probably not box them. And then oops. All right. So here we would have an address. What else? And an amount. So yeah, nothing very fancy here. And that would be an U64. Oops. U64. So does that compile? Not yet. Yeah, sure. Yeah. So let's do that now on the same format. Output, where is that? Here. So this is mod sig locked single deposit, and then we would have this. This would be output. All right. And then here we are doing that. And here I have to import output. All right. And now that's compiling. All right, we are nearly done. We did this part. Then you can see that, as I've told you earlier, we can have a nested payload here. So within a signed transaction, we can have, for example, an indexation payload. that can allow you to tag it in database. We can have signed and unsigned data as well. Yeah, so payload. This is not mandatory, so I'm going to have it as an option, and this would be yeah. So where was I again? Here, no, here. Yeah, and that would be that. Alright, let's see if that compiles. Unresolved, yeah, that's in atomic, of course. Alright, so now I think our unsigned transaction, which is this part, is finished, and we can go to the last part of the signed transaction payload. It's basically made of unlock blocks, and you have to have define an unlock block containing signatures unlocking input. So you have to have as much unlock blocks as you have of inputs, because if you want to consume the inputs, you have to provide an unlocking mechanism for all of them. So you have to provide as much. But one tricky part is that if you have many UTXOs on the same address, for example, you would have to provide the same signature many times. So that's why we have this reference unlock block, which is just a reference to an already existing unlock block. So you could provide only one signature block for that specific address, and then just reference this unlock block so that you don't have this overhead of many signatures being the same. Yeah, so let's start doing that. Let's create once again a new folder called unlock. Let's have mod.rs inside. And we said, yeah, let's just do that. So we have reference, and we have signature. All right. So pub struct signature unlock. And pub struct reference unlock. Alright, and once again here we'll do mod reference and mod signature and pub use reference unlock and could use signature unlock. Oops. Alright, they have a very much different size, so we are going to, oh, why did I put that there? Wait, what? Alright. Yeah, I was saying they have a very much different size. So for the enum, we are going to box them. Pub enum unlock block, and we would have reference being a box of reference unlock, and signature being a box of signature unlock. All right. And then we can yeah, so in the unsigned transaction, no, sorry, where am I? There, yeah, here. Yeah, we haven't started creating this one, so let's do that. So we have that unsigned transaction. Why is it not happy? Syntax error. Yeah, abuse. Yeah, so that's the signed transaction. The first field is the unsigned transaction. So let's do that. Unsigned transaction would be an unsigned transaction. Then we have an unlock block count. Unlock block count. So maybe just 16. And then we have the unlock blocks, which is just a vector of unlock block. And unlock block, so mod unlock and use unlock block. Alright, does it compile? Yes, it does. So now the very last thing that we need to do is to actually fill reference and signature. So what's a reference? It's basically just an index of something, of an unlock block that is before. So reference, where is it? So that's just an index. Let's say again that it's 16, and that's pretty much it. And then we have the signature one. And the signature one is an actual signature. So yeah, it really looks like this. But this time it's not an address, it's a signature. So we'll just replace address with signature. The sizes are different, of course. This is yeah, so this one, yeah, right. So this one, obviously there is no fixed size because it depends on the security of WTS. So this is not sized anymore, but this is a vector of weight. And this one is just a bit more complex because it has a private key and the actual signature. So this is public key. Yeah, so you have to provide the public key and the signature because an ED25 address is actually the hash of the public key, so that you don't reveal the public key. So you have to provide both for a signature. And now this, oops, the signature. And that is 64. Alright, does that compile? Does not. Yes, because of German keyboard. Alright, it does. Yeah, and that was pretty much it. That was the last payload. So I think now, obviously I've been a bit quick because I'm not going into all the details of the RFCs. As you can see, there are a lot of reading to do, so you can do that if you want. But that was just an overview of what it would look like in Rust. I am not doing the serialization and deserialization at the moment because that would be way too long for this video, but it will probably be done In Rust, when you have to deal with serialization and deserialization, you usually use a trait called serde. But in our case, we want to serialize and deserialize to bytes, which is not something handled natively by serde. There is a crate built on top of serde that is called bincode that does exactly that, but you don't have control of the actual encoding, underlying encoding. So if you want to have that kind of control, you have to do the serialization and deserialization yourself. But at the same time, we haven't really settled on an exchange format. So is it protobuf, is it CBOR, is it manual? It could be many things. So since this is not decided at the moment, I'm not investing time in it. I'm just seeing that I haven't actually filled this one, signature unlock. I forgot it, so I'm going to do that. But yeah, this is basically just a signature. Yeah, that's it. Yeah, alright, so as you can see, that's a lot of types, but at the same time it means that the format is extensible, flexible, easily improvable. So yeah, that's a lot of types, a lot of files. Yeah, but that's pretty much it. I'm going to push that on a branch in BP, so you can start playing with it if you want. And over the next week, over the next days or weeks, I will probably start implementing the serialization and deserialization. Yeah, that was it for this week. That's what I wanted to show. So thank you very much for watching, and see you next week for an actual live this time. See you.